Breaking news from beyond our solar system. Comet 3I Atlas is no longer behaving like a typical comet. A few days ago, astronomers noticed that this interstellar visitor had approached the Sun to within 2 astronomical units and began to shine much brighter than previously expected. Its atmosphere expanded to half the diameter of our star, and its glow changed to a disturbing green hue. Moreover, it developed a tail pointing directly at the Sun, which seems utterly impossible. As the speed of travel to Mars increases, researchers admit they cannot explain what is happening. The countdown to overheating has begun, and with each passing hour, this alien wanderer resembles less a comet, becoming a true cosmic mystery that requires clarification. Stay with us until the end of today's research to understand what this news means for our knowledge of space and what happens when alien chemistry finally begins to manifest. Part 1. It becomes larger and brighter. Numbers do not deceive, even when they challenge familiar explanations. In mid-September 2025, astronomers monitoring 3I Atlas noticed something unusual in their data. The brightness measurements began to sharply rise above expected levels, increasing from the predicted values of 15 or 16 to astonishing 12 or 14. For those unfamiliar with the system of astronomical quantities, this represents a significant change. One can imagine that numbers go in reverse order. The smaller the value, the brighter the object. A drop of just 2 magnitudes means that the object now emits 6 times more light than predicted. However, this change did not happen gradually, but rapidly. The database of comet observations, known as COPS, began showing data that steadily rose above the standard upward slope expected for a warming comet. Monitoring from Earth's sky confirmed this trend. The 3I Atlas exceeded all models that astronomers developed for its path to the Sun. A critical moment arrived when the object approached the Sun at a distance of about 2 astronomical units in early or mid-September. For reference, 1 astronomical unit is the distance from Earth to our star, about 93 million miles, and 2 astronomical units is twice that. 3I Atlas was still farther from the Sun than we are, but something fundamental had changed. The acceleration of brightness turned out to be not only unexpected, but also alarming in its intensity. What could have caused such a sudden jump in brightness? The most likely explanation is related to flying ices, frozen carbon dioxide, water, and exotic compounds that have been trapped in the core of the object since its formation around another star. Under the influence of solar radiation, these materials not only melt, but rapidly transition from solid to gas, lifting dust and debris into expanding clouds that reflect sunlight back to Earth. However, there are reasons for concern. Sharp bursts of brightness often indicate instability. Comets that suddenly emit gases can break apart, creating numerous small fragments or impressive clouds of debris. Additionally, they can quickly deplete their volatile materials, leading to their rapid darkening. Being brighter than existing models predict, Comet 3I Atlas tells us that we are witnessing processes that astronomers do not fully understand. However, this is not a reason for global panic. NASA confirmed that 3I Atlas is at a safe distance, never coming closer than 1.8 astronomical units from Earth, which is nearly twice the distance to the Sun. The alarm is not related to a collision possibility, but rather a misunderstanding. We can observe how an interstellar time capsule undergoes fundamental changes in real time as it approaches the inner part of the solar system. Consider the consequences. This object formed in a debris disk around another star, possibly hundreds of light years away from us. It condensed from materials that have never experienced the heat of our Sun and the specific conditions that shaped bodies in our cosmic neighborhood. And now, for the first time in its existence, it encounters the intense radiation environment of our inner solar system. A burst of brightness may indicate the awakening of chemical processes that have remained dormant for millions or even billions of years. Exotic ice, stable in the icy depths of interstellar space, may begin to evaporate for the first time since the formation of this object. We are potentially witnessing the unveiling of chemical signatures from another star system, preserved in pristine form throughout the galaxy. Timeframes give additional significance to this phenomenon. 3I Atlas approaches several critical dates that will determine what astronomers can learn from this unique visitor. On October 3rd, it will come within 30 million kilometers of Mars, close enough for orbiting spacecraft to observe details not visible from Earth. By the end of October, specifically on the 29th and 30th, the comet will reach perihelion, its closest approach to the Sun at a distance of between 1.36 and 1.4 astronomical units. Here, the story takes a troubling turn for observers on Earth. As 3I Atlas approaches its meeting with our star, its position in the sky becomes dangerously close to the dazzling shine of the sun. From early October to early November, the comet enters what is called superior conjunction, a period when the brightness of the sun makes observation nearly impossible from the surface of our planet. This means that the peak activity of our interstellar guest, the moment when solar radiation reaches its maximum strength and the true nature of the comet becomes clear, will largely occur out of our sight. We will have to rely on the mechanical eyes of spacecraft located throughout the solar system, especially those in orbit around Mars, to see what may become the most impressive manifestation of interstellar chemistry in human history. The observed trend of increasing brightness indicates that the three comets will not pass through perihelion unnoticed. Current observations suggest that an object, energized by its encounter with our sun, may be approaching events of flares that will reveal previously unseen details of its structure and composition. However, will these discoveries happen in the weeks when earthly telescopes, blinded by sunlight, captured data obtained in September, painting a picture of an object in a transitional state? Measured brightness values exceeding calculated curves indicate that the three stars are becoming something other than what they were during their long journey through interstellar space. The question is whether this is normal behavior for a comet in an exotic object or something completely unique in our experience with visitors from other star systems. In the coming minutes, we will examine why the coma of this object extends further than usual, why its tail points towards the sun rather than away from it, and how its recent shift to a sinister green glow may signal chemical processes never before observed in interstellar visitors. Riddles multiply as quickly as brightness measurements. But first we need to understand what we are dealing with, as the 3I is not just a comet, but merely the third confirmed visitor from another star system, and its behavior already proves that every interstellar object has its own rules. Part 2. Discoveries and Classification. The story of 3I begins at the height of a mountain in Chile, where automated eyes scan the night sky with mechanical precision, baffling observers. On July 1st, 2025, the asteroid collision warning system, known as ATLAS, detected a faint spot of light moving against the stars. Initially classified as just another small body, this inconspicuous observation soon changed our understanding of interstellar visitors. What makes an object interstellar is not only its origin beyond our solar system, but also the mathematical certainty that it can never be gravitationally bound to our sun. Three bodies move along a hyperbolic trajectory with such force that after completing their arc around our star, they will continue moving through space forever, never to return. The mathematics of orbits is ruthless in its precision. This object moves at such high speed that the gravity of our sun cannot capture it. The designation 3I speaks for itself. The letter I indicates interstellar origin, and the number 3 means it is only the third such object recorded in human history. Its predecessors were 1I 2017 U1, discovered in 2017, and 2I Borisov, found in 2019, each astonishing astronomers with their unique properties that defy simple classification. Now, 3I Atlas continues this tradition of the unpredictability of interstellar objects. The process of its discovery demonstrates how difficult it is to capture such objects. Atlas operates from the Rio Hurtado Observatory, located in the Chilean Atacama Desert, which is part of a global network created to detect potentially hazardous asteroids approaching Earth. The system takes several shots of the same area of the sky over short intervals and then applies computer algorithms to identify anything moving against the stars. On that night in July, Atlas appeared as a barely noticeable line, hardly distinguishable from the thousands of asteroids, comets, and space debris inhabiting our inner solar system. However, images taken before the official unveiling showed that the 3I Atlas had been hidden in astronomical databases for weeks before anyone realized its significance. This delay in recognition is a common phenomenon for interstellar objects, which often appear as asteroids in early observations before showing the blurry lumps and tails characteristic of comets. The initial assessment revealed a dim comet surrounding a central core, indicating that 3I Atlas is something more than just a rocky asteroid. Comets form these blurred atmospheres when sunlight causes the sublimation of ice, creating expanding shells of gas and dust. The presence of a comet at such a distance from the sun, 3 astronomical units, indicates that this object contains volatile substances capable of evaporating even in the cold outer regions of our solar system. As news of the discovery began to spread through the astronomical community, larger telescopes started to take notice of this new interstellar visitor. The Hubble Space Telescope took detailed images in July, and the Very Large Telescope in Chile, along with other ground observatories, also contributed their observations. These subsequent studies revealed that the object is much more complex than the initial images suggested. The size estimates of the 3I Atlas remain uncertain, which is a common problem when studying objects that are too distant and too dim to measure directly. The August update of the Hubble telescope narrowed the core's size to a range from 0.32 to 5.6 kilometers in diameter, illustrating the difficulty in separating the solid core from the surrounding debris. Uncertainty in dimensions is important, as it affects calculations of mass, density, and structural stability of the object, especially as it approaches the intense heat of the sun. Speed calculations provide a clearer picture of the unusual nature of this object. Currently, the 3I Atlas is moving through space at a speed of approximately 130 miles per hour, which is about 50.8 kilometers per second, exceeding any speeds that occur naturally in our solar system. For comparison, the Earth orbits the Sun at a speed of 30 kilometers per second. The speed of the comet will continue to increase under the influence of solar gravity, potentially reaching 68 kilometers per second or over 150 miles per hour. These indicators emphasize the extraterrestrial nature of our visitor. No object formed in our solar system could achieve such speeds without gravitational maneuvers around massive planets. The kinetic signature, 3I Atlas, indicates its interstellar origin, accumulated over millions of years of travel through the galaxy under the influence of stellar gravitational fields and the rotation of the galaxy. The rarity of confirmed interstellar objects makes each of them valuable for science. Until 2017, astronomers had only theoretical models to understand how such objects behave during interstellar travel. One of them, Oumuamua, shattered many assumptions with its elongated shape and mysterious gravitational acceleration. Vyborisov appeared more traditionally like a comet, but its chemical composition turned out to be unique for our solar system. Now, 3I Atlas adds a third data point to this modest collection, and preliminary results show it will be as unique as its predecessors. The object's behavior calls existing models into question in new ways, especially due to its unexpectedly large core and unusual brightness changes. Each interstellar visitor seems to carry its own set of physical and chemical characteristics, indicating a much greater diversity in the processes of forming small bodies in the galaxy than we could ever imagine. The classification process involves not only confirming the interstellar status, but also determining whether 3I Atlas is an object resembling an asteroid, a comet, or something entirely different. The presence of cometary behavior indicates that its properties may resemble those of a comet, but the specific gases and dust composition revealed by spectroscopic analysis will ultimately determine how this object was formed and evolved in its native star system. This is not a local comet ejected from the Oort cloud, a distant reservoir of icy bodies that occasionally sends visitors into our solar system. The body known as 3I Atlas emerged around another star formed from materials subjected to diverse temperatures, pressures, and chemical conditions different from those observed in our cosmic environment. This is a unique example of processes related to planet formation that could have occurred light years away, possibly billions of years ago. Calculations and trajectories indicate that 3I Atlas is on a path that will provide unique observation opportunities, especially during its close passage by Mars on October 3rd. This geometry is not accidental. The tilt of the object's orbit and its temporal characteristics allow spacecraft to observe it precisely when ground telescopes lose sight of it due to sunlight. However, to understand what we are observing, it is not enough to know where the 3I Atlas came from and where it is heading. The real mystery lies in how it will behave when encountering the radiation of our sun for the first time, and why this behavior differs so greatly from theoretical expectations. Part 3. Trajectory and the Temporal School. Time for 3I Atlas, as well as for astronomers striving to unravel its mysteries before it disappears in sunlight, is running out. The mathematics of orbital mechanics outlined a clear route through the inner solar system, marking key dates that will determine what humanity can learn from our third confirmed interstellar visitor. October 3rd, 2020 will mark the first significant milestone when 3I Atlas flies past Mars at a distance of about 30 million kilometers, equivalent to 0.19 to zero point 0.2 astronomical units. In cosmic terms, this is an extremely close approach that will place the interstellar visitor within the range of several spacecraft orbiting the red planet. The moment could not be more fortunate or more complicated. As soon as the 3I Atlas approaches Mars, providing spacecraft with the clearest image of the object, ground telescopes will begin to lose the ability to track it. The rigid geometry of orbital mechanics brings the comet closer to the sun in our sky, creating observational difficulties that will soon become insurmountable. By the end of October, specifically on the 29th and 30th, 3I Atlas will reach perihelion, its closest point to the sun, at a distance of between 1.36 to 140 astronomical units. This distance places him slightly within the average orbital radius of Mars, exposing the interstellar guest to intense solar radiation unmatched in his journey across the galaxy. This moment almost perfectly coincides with the period of greatest observational difficulties from Earth. The evolution of speed creates its own dramatic story. The comet 3I Atlas is currently moving at speeds reaching tens of kilometers per second and will soon reach its maximum speed near perihelion, potentially exceeding 68 kilometers per second, which is about 152,000 miles per hour. In comparison, Earth moves in its stable orbit around the sun at a speed of about 30 kilometers per second. Thus, the 3I Atlas will move more than twice as fast as our planet. These speeds are not just impressive. They illustrate the fundamental physical processes governing interstellar movement. Unlike the objects that appeared in our solar system and gained their speed through gravitational interactions with the sun and planets over billions of years, 3I Atlas carries kinetic energy accumulated during its journey between star systems. Every increase in speed by 1 kilometer per second corresponds to vast distances traveled in interstellar space under the influence of gravitational fields of many stars and the rotation of the galaxy itself. The trajectory of 3I Atlas approaches close to the ecliptic plane, where most planetary orbits are located. This geometry facilitates a close approach to Mars and will ensure a further distant approach to Jupiter in the 26th year. Arbitrary alignment is not a coincidence. Objects approaching from random directions in three-dimensional space are unlikely to pass so closely to several planets during their brief transit through our solar system. Despite being classified as a potentially dangerous object during the initial tracking phase, safety concerns did not arise. The closest approach to Earth will be at a distance of 1/8 of an astronomical unit, almost twice the distance to the Sun, and far beyond any possible threat. NASA's confirmation of the safety of this distance dispelled public fears about a collision, allowing astronomers to focus on scientific opportunities rather than planetary defense issues. However, the real problem lies in the observational geometry. From early October to early November, 3I Atlas faces what astronomers call the superior conjunction, a period when its position in the sky makes observation too difficult due to its proximity to the sun. The angle of solar elongation, or the angular distance between the comet and the sun as observed from Earth, decreases to less than 30 degrees during most of this critical period. Imagine how difficult it is to notice a firefly next to a bright spotlight, and you will begin to understand the problem of observation. Even the most modern telescopes cannot separate the faint light of 3I Atlas from the dazzling glow. Thus, when two objects appear close to each other in the sky, they are difficult to distinguish. This natural limitation in the field of terrestrial astronomy implies that the most active period of a comet may largely occur outside the observer's field of view. The timeline creates a fundamental paradox regarding Comet 3I Atlas. When solar heating reaches its peak, and the comet possibly undergoes the most drastic changes, the astronomical community on Earth finds itself effectively blinded. The peak of gas emission, possible fragmentation events, and maximum tail development may occur on the days and weeks when ground telescopes cannot operate effectively. This gap in observations gives special significance to spacecraft within the solar system, especially those orbiting Mars, the European Mars Express and Trace Gas Orbiter, as well as NASA's Mars Reconnaissance Orbiter and MAVEN, which unexpectedly become humanity's main observers of one of the most significant astronomical events of the decade. After perihelion, the timeline offers hope and a realistic view of what observers can expect. If Comet 3I Atlas successfully survives its solar close approach, ground observations should resume in November or early December when solar intensity becomes less intense. However, by that time, the comet will likely lose most of its volatile substances during an invisible peak of heating. brightness forecasts indicate that even at its brightest phase, 3 and Atlas will remain an object observable through telescopes. Peak brightness readings fluctuate between the 11th and 12th magnitude, which is too faint for the naked eye to observe, but quite accessible for amateur astronomical instruments. The absence of a captivating spectacle to the naked eye may disappoint casual observers, but it does not diminish the scientific value of this unique interstellar event. The speed profile reveals another important aspect of the timeline of Tri and Atlas. As the comet approaches perihelion, its speed continues to increase under the influence of solar gravitational acceleration. However, immediately after the close approach, this same gravity begins to slow the comet as it moves away from the sun. This change in speed affects the duration of the heating peak and the time available for observations with Martian spacecraft. Looking beyond the perihelion, trajectory calculations show that 3I and Atlas will continue their journey through the solar system, eventually approaching Jupiter in March 2026. Although this approach will occur at a significantly greater distance than a flyby of Mars, it may provide additional opportunities for observations from spacecraft as the comet begins its final exit from our solar system. The timeline creates a narrow window of opportunities that astronomy has never faced before. Unlike comets that return regularly, allowing for repeated studies, Comet 3I Atlas offers a unique chance to study an object from another star system. In order for humanity to extract maximum scientific value from this cosmic alien, observational tasks, connection time, and spacecraft capabilities must align perfectly. As critical dates in October approach, the question is not just what the 3I Atlas will reveal, but whether our observational tools will be sufficient to capture these discoveries. Orbital mechanics has set a schedule that waits for no one. Part 4. The expansion and structure of the comet. The most astonishing discovery of 3I Atlas is not its interstellar origin or unusual trajectory, but simply the colossal size of the atmosphere it forms around itself. In September 2025, NASA's Spheric Telescope captured something that contradicted all comet behavior models created by astronomers: an elongated cometary envelope of carbon dioxide reaching 348,000 kilometers from the nucleus. To grasp the scale of this phenomenon, imagine a ghostly atmosphere extending roughly halfway across the diameter of our sun. Comet 3I Atlas has grown so large that it encompasses the entire orbit of Mercury, forming a gas and dust bubble that surpasses anything ever observed around comets in our solar system. This is not just an anomaly. It is an unprecedented case in the history of comet science. A comet forms when solar radiation heats the ice trapped in its core, causing it to sublimate directly from solid to gas, bypassing the liquid phase. This can be imagined as a cosmic snowball evaporating in the sun, although such an analogy does not convey the full brutality of the process. When frozen materials suddenly transition to gas, they carry away dust particles and larger debris, creating an expanding atmosphere that can reach enormous sizes. Comet 3I Atlas tells the story of its formation in conditions vastly different from those in our solar system. The predominance of carbon dioxide over water vapor indicates that this object condensed in a region where carbon dioxide could freeze more easily than water, possibly at the distant edges of a planetary disk of another star, where the temperature remained low enough for carbon dioxide stability, while water mostly existed as vapor. This carbon dioxide wealth hints at the chemical conditions that prevailed during the formation of 3I Atlas. In most comets of our solar system, water is the primary volatile component, while carbon dioxide plays a secondary role. The inverse relationship observed in 3I Atlas indicates temperatures and pressures of formation unmatched by known objects in our cosmic vicinity. The composition of the comet is just one of its astonishing features. Images from the Hubble Space Telescope and ground observatories demonstrate a structure that challenges fundamental ideas about the behavior of comets. Instead of the usual tail pointing away from the sun, Comet 3I Atlas exhibits what astronomers call an anti-tail, a stream of material that appears to be moving towards the star. This structure, directed towards the sun, presents a mystery that scientists work on during sleepless nights. Traditional views of comet physics assert that solar radiation pressure should push gas and dust away from the sun, creating familiar tails that have inspired people for millennia. However, Atlas seems to violate this principle, ejecting material in directions contrary to educational explanations. Observations from Hubble on July 21st recorded what scientists described as a front-lit, fan-shaped structure, extending from the core towards the sun, rather than away from it. Subsequent images obtained by the Gemini and South telescopes on August 27th confirmed that this unusual geometry persists and evolves, indicating that the anti-tail is a stable feature, rather than a temporary anomaly. The physical processes underlying the formation of an anti-tail are more complex than simple radiation pressure. Large dust particles, too massive to be easily pushed away by solar photons, can maintain trajectories towards the sun if ejected from the nucleus with sufficient initial velocity. Moreover, projection effects can create the illusion that material moving in three-dimensional space is directed towards the sun when viewed from a certain point on Earth. However, theoretical models struggle to explain the stability and prominence of the solar jet stream of Comet 3I Atlas. The structure appears too clear and durable to be a mere result of projection effects, as the sizes of dust grains and ejection speeds required to form such a large anti-tail exceed what is physically plausible for a comet nucleus. Recent studies suggest that an anti-tail may be a result of unusual rotation conditions or unique surface properties characteristic of interstellar objects. A slowly rotating core can maintain temperature differences between its day and night sides, leading to a concentration of gas emissions in certain directions. Moreover, the surface composition of Comet 3I Atlas may include materials that react to solar heating in ways unfamiliar to researchers studying local comets. The expansion speed of the coma adds another layer of complexity to this mystery. Spectroscopic observations show that the gas speeds in the coma exceed typical values for comets at similar distances from the sun. Enhanced gas emissions may result from the release of super volatile compounds that remain stable only in interstellar environments and quickly sublimate upon first exposure to significant solar heat. Measurements of the coma reveal additional anomalies. The gas temperatures recorded through infrared observations indicate heating mechanisms that go beyond simple absorption of solar radiation. Perhaps the explanations lie in the chemical reactions between previously separated compounds or in the release of energy stored in the exotic structures of ice crystals formed in interstellar space. The three-dimensional structure of the coma, reconstructed considering various angles of view and wavelengths of light, demonstrates symmetry, indicating uneven gas emission from the surface of the nucleus. Instead of the relatively symmetrical jets typical of well-studied comets, Tri-I Ethles exhibit streams and fans of material emanating from specific areas of its core. These jets indicate that the core's surface contains distinct areas rich in volatile compounds, possibly exposed due to impacts or thermal cycles during the object's interstellar journey. The gas emission model can preserve information about the conditions of comet formation and its subsequent evolution over millions of years of cosmic travel. Analyzing the dust in the coma reveals a particle-size distribution different from that observed in comets of our solar system. The vastness of the large grains necessary for the formation of the observed anti-tail structure suggests that Tri-I Ethles either formed with a different dust-to-gas ratio than local comets, or its particles underwent modifications during interstellar transit. The dynamics of expansion show temporal variations that correlate with the distance of the comet from the sun, and possibly with its rotation periods. As Tri-I Atlas approaches perihelion, the coma continues to grow and develop, likely reaching even larger sizes with increased solar heating. Modeling to predict the future evolution of a comet's coma faces unprecedented challenges. The unusual composition, geometry of the anti-tail, and increased gas ejection speeds require modifications to standard cometary physics models. Researchers are actively developing new theoretical models in real time as observations continue to reveal unexpected phenomena. The consequences extend beyond the comet Tri-I Ethels. If interstellar comets like this one exhibit such unusual coma characteristics, it may mean that our understanding of comet physics, primarily based on objects from our solar system, represents only a narrow fragment of possible phenomena. Every interstellar guest has the potential to change our understanding of how such objects form and evolve. As the Tri-I Ethles comet approaches critical points of proximity to Mars and the Sun, the further evolution of its coma will be an important test for various theoretical models. The question is whether significant changes will occur at a time when ground-based telescopes can no longer track the behavior of the comet. However, the change in the coma is just one aspect of the transformation of Tri-I Atlas during its interaction with solar radiation. The most notable event was mid-September when the comet began to glow with a bright green light, signaling chemical processes never before observed in interstellar objects. In mid-September 2025, Tri-I Ethles caused a real sensation in the astronomical community. It turned green. Not gradually, but with a bright emerald glow that transformed this interstellar object from a pale spot into something almost alive against the backdrop of stellar emptiness. The change in color was not immediately noticed by casual observers. Tri-I Ethles remained too dim for the naked eye, but sensitive cameras mounted on telescopes around the world began to take pictures showing a distinct green hue around the comet's core. This transformation became especially noticeable in the photographs taken during the lunar eclipse on September 14th, when the shadow of the moon created a darker sky, enhancing the contrast of the comet's new glow. Green rays of light tell a story written in the language of quantum mechanics and molecular chemistry. When certain molecules absorb ultraviolet radiation from the sun, their electrons transition to a higher energy state. Returning to their fundamental state, electrons emit light at specific wavelengths, which our eyes perceive as different colors. In the case of tri-I ethers, the green glow is likely caused by diatomic carbon, two carbon atoms bonded together, denoted as C2 in chemical notation. Diatomic carbon acts like a molecular neon sign in the endless cosmos. Under the influence of solar ultraviolet radiation, C2 molecules emit light at a wavelength of about 516 nanometers, creating a characteristic green glow that made Tri-I Atlas one of the most noticeable comets in recent years. This process of emission, called fluorescence, converts invisible solar energy into visible light that can travel millions of kilometers, reaching ground-based telescopes. But here is where the story becomes mysterious. Early spectroscopic observations of Tri-I ethers showed relatively few signs of carbon-containing compounds. The initial chemical analysis showed that carbon dioxide and water vapor predominated, with only trace amounts of carbon-containing molecules typically responsible for the green hues of comets. This apparent contradiction between the observed green glow and the established chemical composition raises many questions for researchers about what is happening in the expanding atmosphere of the comet. One possible explanation is related to phase transitions in the behavior of gas released from a comet. As Comet 3I Atlas approached the Sun and crossed the 2 astronomical unit mark in early September, intensified solar heating could have triggered the sublimation of previously